Hello, everybody. Today we have a pleasure to have a talk by Robert Brandenberger. He's a professor in McGill University. He will tell us about non-singular cosmologies and black hole from S-Branes. Robert, please, 1 hour.
So thank you very much to the organizers for inviting me to speak. So I will try to convince you in this talk that S-Branes can lead you to singularity resolution in cosmology and black holes. So I'm a cosmologist, so I will spend most of my time on showing you the non-singular cosmology construction with S-Branes. And then at the end, I will move to the discussion of S-Branes and non-singular black holes. But let me start with an introduction. So you all know that in the context of general relativity, there are the famous Hawking-Penrose singularity theorems. So if you have a solution to the Einstein field equations for metric and matter satisfies the null energy condition, and you have some technical assumptions, which are listed here, that then space-time is geodesically incomplete, so singular. And prime examples for that is the Big Bang singularity of standard Big Bang cosmology. So this is a Penrose diagram of standard Big Bang cosmology. You have the initial time singular Cauchy surface. And the other prime example is the singularity at the center of a Schwarzschild black hole. So now the way that I've shown these two pictures, it sort of indicates that if you manage to resolve singularities, it might be possible to have a construction in which the center of the black hole, the inside of the black hole, connects to the beginning of a new universe. So this it's been an idea for a long time, in particular in Russia, the idea that there could be a universe inside of a black hole. Good. So now what I will try to convince you of in this talk is that with some new ingredients from superstring theory, you might be able to realize this hope. So superstring theory is different than standard field theory in that the fundamental constituents are strings and not point particles. And in my opinion, this inevitably will lead to a breakdown of effective field theory if we try to apply it to the context in which string theory is fundamental. So the singularity theorems don't obviously apply. And so there's a chance to obtain non-singular cosmology and non-singular black holes. So to elaborate on this point, let me assume for the moment that space is a torus with radius r. In that case, there are quite a lot of different string states. There are momentum modes, the center of mass motion modes, the modes that would also exist in point particle theories, and their energies are quantized in units of 1 over r, where r is the radius of the torus. But then strings can do things that point particles cannot do. Strings can wind space, and the energy of winding modes is quantized in units of r, because the more times that a string winds space, the heavier it is. And then strings have lots of oscillatory modes, and their energies are independent of r. So at low densities and low curvatures, only the low energy degrees of freedom are excited, and these are the momentum modes. So in this context, point particle effective field theory is applicable. However, when the energy scale or the curvature scale approaches the string scale, then oscillatory modes and winding modes can be excited. And this will lead you to the breakdown of point particle effective field theory. So now if you want to maintain a effective point particle field theory description, you can try to include the stringy degrees of freedom in a particular way, and this gives rise to the S-Branes. So the idea is as follows. at the string energy scale or curvature scale, a new tower of string states becomes comparably massed to the usual energy degrees of freedom. And the new tower of states, you should view these as the winding modes and the oscillator modes, which I just described. And if you want to keep your effective field theory description, then you must include these new degrees of freedom in your effective action. And you can postulate that the new term is localized exactly on the space-like hypersurface where the string energy scale is reached. And a term in the low energy effective action localized on a space-like hypersurface, this is what I call the S-brane. So this is the way that you should view the modified low energy effective action. So S0 is the action that you started with, point particle effective action. And once you reach the string energy scale, string curvature scale, you have to add this term delta S. And this term delta S is localized on this hypersurface. And it is a relativistic object, so it is given by its tension, kappa. And I will take kappa to be given by the string scale. So this is what I mean by an S-brane. So now if you use the intuition coming from topological defects, and I've done quite a bit of work on topological defects, then you will realize that the energy density of an S-brane is 0, because the energy density corresponds to the component of T mu nu, which is perpendicular to the surface where the brane is localized. And so similar to how a domain wall has no pressure in perpendicular direction, the S-brane will have vanishing energy density. And since it's a relativistic object, its T mu nu in the spatial directions will correspond to tension, and that's negative pressure. And so you see immediately that you have a violation of the null energy condition, which is given by this new term. And so you can ask the question, can S-branes mediate singularity resolution? And so this is a question which I'm going to answer in the affirmative in the next section. And the next section is a long section. So here, so I'll show you that with S-branes, you can obtain a non-singular equiparodic cosmology. And I have a sub-story here in this section. And my sub-story is that there is more than just one early universe scenario, which is consistent with our current observation. We don't just have inflation, but there are alternatives to inflation. And in fact, from the quantum gravity point of view, I actually think that inflation has some serious conceptual problems, which bouncing cosmologies may not have. So this is a subplot in the story. So I'll first remind you of the data that we need to explain. I will establish the criteria for successful early universe cosmology. I'll give you 3 scenarios, and then I will focus on the bouncing cosmology, which we want to render non-singular via S-branes. So this is what I want to do in this part of the lecture. So data. So we need to explain the isotropy of the cosmic microwave background. So this is a map of the sky projected onto a plane. The intensity of the microwave background is converted to temperature and is plotted here. We have isotropic microwave background. And if you look at better than 1 part 10 to the 4 of this temperature, you start to see anisotropies, hot spots and cold spots. And this data you can quantify. You can expand this map in spherical harmonics. You can plot the power as a function of angular scale. And the data is the black dots with the statistical uncertainties on small angular scales and some systematic uncertainty on large angular scales. And this red curve is a 6-parameter fit to the data, which fits the data quite well. And I'm now going to tell you who are the people who first constructed this red curve. Good. So now I want to remind you that in standard Big Bang cosmology, so if we describe space, time, and matter classically, then we cannot explain any of this beautiful data. So, for example, so the microwave background is released 300,000 years after this initial fireball. The universe is 13.7 billion years. And so the time interval from the hot Big Bang to this recombination surface is very, very short compared to the time between recombination and the present time. And this means that the distance, which could have been in causal contact at the time of recombination, starting at the singularity, is much, much smaller than the distance over which we view isotropy. So here, the vertical axis is time, horizontal axis is space, and this is the region of causal contact, but this is the region over which we observe isotropy of the microwave background. So this is the horizon problem of the standard Big Bang model. And here is a similar plot, vertical axis time, horizontal axis is space. Here I'm using co-moving coordinates, coordinates which expand as space expands. And here I'm showing the wavelength of a fluctuation, which we observe today, for example, the quadrupole of the microwave background. And the wavelength is larger than the horizon at the time of equal matter and radiation, or the time of recombination, and therefore we cannot causally explain the origin of these fluctuations. So hence, in order to come up with an explanation for what we see, we need to modify the history of the universe at very early times, before the time of nucleosynthesis. So we want to explain this data. And the people who first discussed the physics that can explain this data, these are Zhdovich and Zuniyaev in Moscow, and Peebles and Yu in Princeton. And they did that in 1969, 1970, 10 years before the development of inflation. And here's a plot from the paper by Zhdovich and Zuniyaev, the first half of the plot. So the vertical axis is time, horizontal axis is space, my co-moving coordinates. This diagonal curve is the standard Big Bang horizon. And here is illustrated two different wavelengths, large-scale fluctuations, small-scale fluctuations. Now, fluctuations you should visualize as plane wave, small amplitude inhomogeneities. They are frozen in while the wavelength is larger than the standard Big Bang horizon, what technically speaking at the Hubble radius, and they start to oscillate when the wavelength becomes smaller than this Hubble radius. So the wavelength which just crosses the Hubble radius at recombination, it has had no time to oscillate, and we catch the wave at maximal extent, and this maximal density wave will produce a maximum of the induced microwave background anisotropies. A wavelength which has done a quarter of an oscillation, we will catch it when it has zero extent. When it's only a velocity perturbation, it will be a minimum of the microwave anisotropies. So this picture, which was very well understood back in 1970, it explains the physics that goes into this curve, the acoustic oscillations of the cosmic microwave background. And this figure has a second part, figure 1b. And this figure 1b is the amplitude of matter fluctuations as a function of wavelength. And you see the same oscillations produce oscillations in the power spectrum of density waves, of matter waves. And these are called baryon acoustic oscillations. So the acoustic oscillations in the microwave background and the baryon acoustic oscillations, these were first measured in approximately 2000. They were well understood already. Their origin was well understood already in 1970, 10 years before inflation. So the one question which was not addressed back in 1970 is how does one obtain a spectrum of density waves which look to be acausal from the point of view of standard Big Bang cosmology? Because you see, they are on scales larger than the standard Big Bang horizon. And this is indeed where inflationary cosmology provided the first scenario based on causal physics, which yields such a spectrum. But it is not the only one. And so now I'll try to give you the criteria for a successful early universe cosmology. So if you have a new theory of quantum gravity and you want to connect your new theory of quantum gravity with observations, your new theory of quantum gravity should give you an early universe which is consistent with the three criteria which I'm going to establish. So first of all, I want to emphasize the difference between horizon and Hubble radius. The horizon is the region of causal contact. It tells you how far light can travel from the beginning of time. Whereas the Hubble radius is a local concept. It is the inverse expansion rate. And it simply divides scales on which fluctuations oscillate from scales where fluctuations are frozen in. Now, in standard Big Bang cosmology, the two are the same, and therefore you have the problems. And so in any theory which can provide a mechanism for the origin of structure and a mechanism to solve the horizon problem, the Hubble radius has to be different than the horizon. So here are the three criteria for a successful early universe cosmology. The horizon has to be much bigger than the Hubble radius in order to explain the isotropy of the microwave background. And then scales that we observe today have to originate inside the Hubble radius at early times. Otherwise, we can construct a locally causal mechanism to generate these fluctuations. And finally, the mechanism also has to generate an approximately scale invariant spectrum of these perturbations. So these are the three criteria for a successful early universe cosmology. And inflation is indeed a scenario where all these three are satisfied. So I'm sure all of you know about inflation, but this is the idea that there's a phase in the early universe from time t sub I to time t sub r, when space expands exponentially. During this time, the horizon expands exponentially, whereas the Hubble radius is constant. And so since the horizon becomes exponentially larger than the Hubble radius, you can easily explain the isotropy of the microwave background. And if inflation lasts long enough, then scales that we observe today start out inside of the Hubble radius at the beginning of inflation, and we can come up with a causal generation mechanism. And the fact that you have a time translation symmetry in this inflationary phase guarantees that you get a scale invariant spectrum of perturbations. But here's another way to satisfy all these, the three criteria. You have a bounce in cosmology. So here I'm drawing the cosmological scale factor as a function of time. And I will have a contracting phase like in standard Big Bang cosmology, just the mirror inverse of it. The expanding phase of standard Big Bang cosmology. And I have a new phase which mediates between contraction and expansion. And this is going to be realized in our construction by the S-Brane. So this is the corresponding space-time sketch. So my co-moving spatial coordinates versus time. This is the bounce time. This is the Hubble radius. And the horizon is infinite because time runs from minus infinity to plus infinity. So no problem explaining the isotropy of the microwave background. And if you go far enough back in time, all scales that we observe today start out sub-Hubble. Therefore, it's possible to come up with a causal generation mechanism. And I'll come back to that a little bit later, how that generates a scale invariant spectrum. Finally, you also have the idea of an emergent universe where you have a new phase, which can be modeled as, for example, as a quasi-static phase, a phase transition to standard cosmology expansion. This is the corresponding space-time diagram. And you see again, time runs from minus infinity to plus infinity. So criterion 1 satisfied. Scales that we observe today start out inside the Hubble radius in the emergent phase. So criterion 2 satisfied. But today I'm not talking about the emergent universe. Okay, now from the point of view of quantum gravity, I want to mention this issue, what we called 20 years ago, the Transplunkian problem for inflation. So if inflation lasts just a little bit longer than it needs to in order to be successful, then the wavelengths of all scales that we observe today start out at early times in the Transplunkian sea of ignorance. They start with wavelength smaller than the Planck length. So this was a discussion 20 years ago. And then 2 years ago, Prof and Bedroya, based on our previous analysis, postulated that no consistent cosmology can admit a feature that Transplunkian modes exit the Hubble horizon. So given this usual parameterization of cosmology, the Transplunkian censorship conjecture says that if you start at some initial time Ti with the Planck length, you evolve the Planck length to a later time, T sub r. This length that you get must be smaller than the Hubble radius at a later time. So this is the postulate. And I want to motivate this postulate in analogy with Penrose's cosmic censorship hypothesis. So Penrose says that general relativity allows for pathological solutions with time-like singularities, which are not hidden from an observer. For example, black holes with charge greater than a mass. So there's no problem constructing these solutions in general relativity. But the Cauchy problem is not well defined for an observer external to these black holes, and there are unitarity problems. So Penrose would say that the theory that completes general relativity should prohibit these pathological solutions. So Penrose says that the ultraviolet physics that completes general relativity has to have the feature that the external observer is shielded from a time-like singularity by a horizon. So let's take this Penrose cosmic censorship hypothesis and let's translate it from black hole physics to cosmology. So we take position.
Robert, can I ask a question?
Yeah.
So, I mean, you say that, can you go to the previous slide, the Penrose? I mean, whatever the UV physics should, I mean, if a consistent UV physics should avoid singularities, right? Then why?
No, I'm saying something milder. So
Okay.
I agree with you that consistent UV physics should avoid singularities, but this is a much milder statement. It's a statement that if there is a singularity, it needs to be, the observer should be shielded.
Okay.
And
another short question, I mean, about Transplunkian problem. How many folds you require, I mean, prior to 60, the typical number 60, to hit the Transplunkian physics? I mean,
only 10 more. So if you use inflation at the grand unification scale, which you ought to if you don't want to fine-tune particle physics, then if inflation lasts more than 70, you run into a problem.
Okay.
Thanks. Good. So now we will translate Penrose's cosmic censorship hypothesis to the context of cosmology. So position space becomes momentum space. The singularity becomes the set of Transplunkian modes, and the black hole horizon becomes the Hubble horizon. And so Penrose's hypothesis translated under this translation scheme becomes the statement that an observer measuring super Hubble horizon modes must be shielded from effects of Transplunkian modes. Okay, now why do we use the Hubble horizon as a generalization of
Just small comment. I don't know. In the case of black holes, there is no problem with Transplunkian mode. So why it appears only in the context of cosmology?
Well, this is this is my translation scheme. So the region of ignorance is the Transplunkian modes. And in an expanded universe, the wavelength increases. So there's a possibility that Transplunkian wavelengths becomes large.
That is true. And of course, if you modify the dispersion relation, right? So suppose if you have the standard dispersion relation,
that we played around with. See, 20 years ago, there was quite a bit of work on modifying the dispersion relations and studying what that would do. But here, I don't want to go that route. I want to adopt this sensitive conjecture. Okay. And this will mean that an observer measuring super horizon modes must be shielded from Transplunkian modes. Okay.
Okay.
Now, the reason that I'm choosing the Hubble horizon as opposed to some other surface is that the fluctuations only oscillate on sub-Hubble scales and fluctuations freeze out and become classical on super-Hubble scales. So I'm demanding that the classical region be insensitive to the Transplunkian modes. So that's a mild assumption. Maybe there's a more stringent version of the Transplunkian sensitive conjecture. Anyway, so if you accept this, and I'm not going to ask you to accept this, but if you accept this, then you find a serious problem for inflation. Because inflation, to be consistent with the Transplunkian sensitive conjecture, cannot have the initial Planck length at the beginning of inflation becoming bigger than the Hubble radius at the end of inflation. So here I've drawn inflation to be marginally consistent with the sensitive conjecture. But if inflation is to be successful, then the current Hubble radius has to emerge from inside of the Hubble radius. Otherwise, inflation is not predictive. So the TCC sets an upper bound on the duration of inflation. Inflation being successful sets a lower bound on the duration of inflation. And whether these are consistent or not depends on where the Hubble radius is localized relative to the Planck length. And the lower the energy scale of inflation, the easier it is to satisfy the criteria. And so this is the upper bound on inflation from the Transplunkian sensitive conjecture. This is the lower bound on the amount of inflation by demanding that the current Hubble radius emerges from inside the Hubble radius at the beginning of inflation. And if you mix these two together, if you combine these two equations, you find that they're only consistent if the energy scale of inflation is 6 orders of magnitude lower than what we would like it to be. And in particular, that means completely negligible spectrum of primordial gravitational waves. Okay, now bouncing cosmologies and emergent cosmologies are consistent with the Transplunkian sensitive conjecture as long as the energy scale of the bounce or the energy scale of the emergent phase is lower than the Planck length. So in a sense, these alternatives to inflation might have advantages compared to inflation. But anyway, even if you don't accept this, please keep an open mind and let us see if we can construct a viable bouncing cosmology. So I will turn to the question of constructing a viable bouncing cosmology using S-Branes. And I will take the ekpyrotic bouncing scenario. And the ekpyrotic bouncing scenario means that the contracting phase is a phase of very slow contraction. So this is the idea of ekpyrosis. Now, among bouncing models, the ekpyrotic scenario has distinct advantages because it dilutes anisotropies, it creates spatial flatness, and it is an attractor in initial condition space. And these are all features which other bouncing cosmologies do not have. And these are nice features which the ekpyrotic scenario has in common with large field inflation. Okay, so this is the idea of ekpyrosis. Now, how do we get ekpyrosis? So what we want is we want the scalar field. We want the scale factor to be very slowly contracting. So it grows as a power law with a very small power. And in terms of conformal time, it's also described by a small power. The power is p over 1 minus p. Now, this scale factor can be obtained if we use general relativity and we have a scalar field with a negative exponential potential of this form. So it is a fairly steep negative exponential potential. So p is very small, so this means that the potential is quite steep. Now, negative exponential potentials arise ubiquitously in superstring theory, maybe not necessarily with such a very steep potential, but with a potential which is not flat. Okay, so if we take such a potential and we look at how the scalar field evolves when it is on the ekpyrotic homogeneous trajectory, we find this solution of the Klein-Gordon equation in the contracting universe. And here I just want you to pay attention to this prefactor. So phi of t is a very small number times m Planck. So in contrast to inflation, where the scalar field evolves for a long distance on Planck length, in the ekpyrotic scenario, it evolves a short distance in Planck length. So to be specific, if we consider 1 Hubble time, then the field evolves a distance much, much smaller than a Planck length. The potential is quite steep. So it means that V prime over V prime is a derivative of the potential with respect to the field, in Planck units is much bigger than 1. And the relative curvature is also bigger than 1, which means that ekpyrotic potentials are also completely safe from the swampland constraints, which you might have heard of. So the swampland program asks under which conditions scalar fields coming from string theory, scalar fields of effective field theories can come from string theory. And you see that the swampland constraints tell us that as long as the field range is much smaller than a Planck value, and as long as you deal with steep potentials or tachyonic potentials, then you are safe. So in ekpyrosis, you are safe against the swampland conditions. And here's a reference to a recent paper where we've worked this out directly. So in this paper, we generalize the swampland criteria to the case of a contracting universe. So anyway, the bottom line is that the ekpyrotic scenario among bouncing scenarios has advantages. However, the ekpyrotic scenario has challenges. How do we get the bounce? The bounce. The transition from contraction to expansion. And do we obtain a spectrum of almost scalar invariant cosmological perturbations? And what about gravitational waves? What predictions for gravitational waves do we get? Now, in previous realizations of the ekpyrotic scenario, one required extra new matter fields to obtain a non-singular bounce. And there are all kinds of problems with ghosts and other instabilities. And we also required extra matter fields just to obtain approximately scalar invariant cosmological perturbations. And if one had these features, one generically obtained a negligible spectrum of gravitational waves. And so here I'm going to propose a model in which we realize the ekpyrotic bounce using an S-Brane. So this is work that I did with a PhD student of mine, Ziwei Wang, who's graduated and who's actually going to Japan, to Kobe, beginning, I think, in February. So results, we've shown that the S-Brane can mediate a continuous bounce, not a differentiable bounce, but a continuous bounce, that the gravitational waves passing through the brain, through this S-Brane, acquire scalar invariant spectrum with a small blue tilt. And that if the S-Brane has zero shear, then you get scalar invariant spectrum of curvature perturbations. And in our model, we get two consistency relations between the four basic cosmological observations. So our model is predictive. the S-Branes scenario, superstring theory makes testable predictions for cosmological observations. And if you don't like superstring theory, you can try to construct your own quantum gravity model, and you might be able to connect it with observations in a similar way that I'm doing and come up with predictions of your model. So I'll show you how these predictions for the S-brane ekpyrosis come about. So again, we consider this contracting universe. The energy density is increasing. And once the energy density reaches a string scale, then this new tower of string states becomes comparable in mass to the ones that we started out with. They must be included in the low energy effective action. And we will postulate that we can do it by a term which is localized on a space-like hypersurface. Now, this is only consistent if the universe starts to expand after reaching the space-like hypersurface. Otherwise, my assumption that the new term is localized on a space-like hypersurface would not even be self-consistent. But I will show that with this assumption that we have an S-brane on a space-like hypersurface, we can get the transition between contraction and expansion. And therefore, this ansatz is at least self-consistent. Okay, so this is how we do it. This is the action that we take. We take the usual Einstein action coupled to the scalar field with a negative exponential potential, and we add this S-brane term, whose tension is given by the string scale. Okay, so now again, since we have vanishing T mu nu perpendicular to the surface, we have vanishing energy density, we have negative pressure, so therefore the dominant energy condition is violated. And from the point of view of singularity theorems, it is now possible to obtain a non-singular cosmology. It is possible to obtain a bouncing cosmology, and I will show you that this indeed works. Okay, so I've shown you the action, and now what we want to do is we want to match the contracting ekpyrotic phase with an expanding standard Big Bang model phase by using the Israel matching conditions across the S-brane surface. And Israel tells us that we need to have continuity of the induced metric, and we need to have a jump in the extrinsic curvature, which is given by the tension of the S-brane. So the matching conditions tell us that the delta H, the change in the Hubble constant across the S-brane, is given in this way by the S-brane tension. And so you see that if the S-brane tension is high enough, you can make the Hubble constant after the S-brane positive, even if H is negative before. So this is what delta H, what we want delta H to be if you want immediate transition between string energy scale contracting phase and string energy scale expanding phase. And you can get that if this prefactor n in front of the S-brane tension has this value. So this is what the background does. So let me summarize what I just hope to have shown you. I hope to have shown you that for sufficiently large tensions, the S-brane mediates a transition between contraction and expansion. So now you can ask what happens to gravitational waves and what happens to density perturbations during the in this transition. And let's look at what happens first to gravitational waves and density perturbations during the phase of ekpyrotic contraction. So this is the metric, the cosmological metric, which includes gravitational waves. H is a gravitational wave amplitude. The rescaled gravitational wave amplitude satisfies this standard equation, which Starobinsky studied a long time ago in great detail. And in the context of ekpyrotic contraction, the dominant solution on scales larger than the Hubble radius decreases very, very slowly, which means that the spectrum of these gravitational waves hardly changes in the contracting phase. And if you start with a vacuum spectrum, the vacuum spectrum remains approximately vacuum with a slight blue tilt. What happens to density perturbations? So the density perturbations are parameterized by this variable phi that appears in the metric. The Sasaki, it's related to the Sasaki-Mukhanov variable. This is the Sasaki-Mukhanov variable. Now, if you look at the equation of motion for the Sasaki-Mukhanov variable, you find the same equation of motion as for gravitational waves. And therefore, you find that in this ekparotic phase of contraction, the fluctuations of the Sasaki-Mukhanov variable is vacuum with a slight blue tilt and not at all scale invariant. But there's a second view, and the second view directly focuses on the variable that we measure, which is the phi, or the rescaled phi. And this variable satisfies this modified equation of motion, and therefore it has modified solutions. And in fact, if you look at these solutions, then with vacuum initial conditions, you find that on scales larger than the Hubble radius, this initial vacuum spectrum is transformed into a scale invariant spectrum with a slight red tilt in exactly the same way that in inflation, the perturbations become scale invariant with a slight red tilt. So this is what was already well known. And the key question is, what happens when during the S-Brane bounce? So which variable passes through the S-Brane bounce continuously? So previous models in which we modeled the transition using effective field theory with matter violating the null energy condition, so differentiable bounces, it usually gave us the fact that it is the Sasaki-Mukhanov variable which passes through the bounce without change. However, Duro and Vernizzi in this very important paper show that if you have a matching surface, then for generic space-like matching surfaces, usually it is this Vardin variable which passes through the bounce continuously. Okay, so what did we do? And since most of you are not cosmologists, I will go through the next couple of slides rather quickly. So this is the equation of motion for the rescaled gravitational wave amplitude passing through the S-Brane bounce. So this is a nice equation. I like it because it is an equation which one in Russia one would call this an equation involving generalized functions. In the West, one would call it involving distributions. Okay, and so one can study this equation by studying the solutions before and after the delta function singularity, and then matching the solutions across the singularity, taking into account this source term. So this is standard way of solving ordinary differential equations with a distributional source. And what you get is you get Bogoliubov mode mixing across the transition. And I was very surprised that you find that the Bogoliubov mode mixing coefficients have the feature that they scale as m over k. So the smaller the frequency, the larger the Bogoliubov mode mixing coefficient. And this is precisely the factor which transforms a vacuum spectrum into a scale invariant one. So what we found, using just this basic equation of motion for gravitational waves, passing through the S-Brane, nothing else, we found that the spectrum of gravitational waves after passing through the S-Brane is scale invariant with a slight blue tilt. And we haven't yet measured the spectrum of gravitational waves, so this slight blue tilt is a prediction. Inflation predicts a slight red tilt. And this is the equation for the power spectrum. This gives you both the amplitude and the tilt. Okay. Now for the density perturbations, for the curvature perturbations, you can do the same thing. You can use the matching conditions of Duhamel and Mukhanov to connect solutions of the cosmological perturbations before the bounce, before the S-Brane bounce, to those after the S-Brane bounce. So it's a second order differential equation. You always have two solutions. One solution is constant in time. And what the matching conditions show is that the growing solution in the contracting phase matches non-trivially with the dominant solution in the expanding phase. And therefore, it is the scale invariant part of the spectrum of phi at the end of a contracting phase, which becomes the scale invariant spectrum of cosmological perturbations in the expanding phase. So here are the details. This is the relation between these coefficients of the modes. This is the relation between the dominant solution in the contracting phase, which has a scale invariant spectrum, and the dominant solution in the expanding phase, which acquires the scale invariant spectrum. Here's the initial amplitude you start out with. Then we get the final amplitude, and this gives us this prediction for the amplitude of the cosmological perturbations. Scale invariant with a slight red tilt, completely consistent with observations. Okay, so we have two predictions. We have a prediction for the amplitude of gravitational waves divided by the amplitude of cosmological perturbations. This is this R. And we have an amplitude which relates the tilt of the gravitational waves to the tilt of the density perturbations. The tilts are defined this way. So we are making two predictions for cosmological observations based on this model, which includes quantum gravity effects. So let me summarize this part of the talk, which is most of the talk. So I hope to have shown you that with an S-Brane, you can obtain a continuous transition between a phase of ekpyrotic contraction and the radiation phase of expanding Big Bang cosmology. And when I say radiation phase, what I mean is the following. After the S-Brane, it was created during the contracting phase. It decays, not into the same stuff that was there before. In fact, we've been able to show that it decays typically into radiation. And so this is a direct way of generating the radiation after the phase of contraction. This is this reference. So we get postdictions. We find a scale invariant spectrum of curvature fluctuations with a slight red tilt. This is consistent with current observations. And the prediction is the scale invariant spectrum of gravitational waves. This is also predicted by inflation. We predict a slight blue tilt. This is not what standard inflation predicts. So let me move on and spend maybe 5 minutes, maybe even a little bit less, on how to apply these ideas to black holes. So I'm going to start again with the action for standard gravity plus matter. This is supposed to be true to the outside of the black hole horizon and maybe even inside the black hole horizon until somewhere near the singularity. So we have Einstein gravity plus some matter. And now we want to set matter in its ground state outside of the black hole. And then we will argue that once the Weyl curvature reaches string scale, then the effective theory will break down. And we have to add a S-Brane, which is localized at the value of R, which is the space-like surface inside of the horizon, where the Weyl curvature is equal to the string scale. So this is the action which we're going to work with. And outside of the black hole, and for radii larger than this radius R0, which is given when the Weyl curvature scale becomes a string scale, then we make this usual Schwarzschild ansatz for the metric. And if we start with no matter outside, then we indeed get this form of f of r. And then to the future of this surface r equals r sub 0, we will make the cosmological ansatz. we will make the ansatz for an anisotropic cosmological metric. So this is for r smaller than r0. I remind you that r is the time inside of the Hubble radius. So we make this ansatz for and this is a cosmological metric. And it is anisotropic because the 3 dimensions of space inside of a black hole are highly anisotropic. Okay, now we will match across actually, you see, this equation is completely wrong because I copied the wrong equation from my tech file. This should have been a standard, no, sorry, this is correct. No, I copied the wrong equation. Sorry about that. You should replace this by an anisotropic Friedmann metric with scale factor A. A scale factor A in the t direction and a scale factor B in the directions which correspond to the omegas, to the compact, to the S2. So the cosmological metric has one scale factor associated with R, with R, which is the time. No, sorry, one scale factor associated with the time, which is the radial coordinate of the Schwarzschild, and one scale factor associated with the S2. So these are the 2 scale factors, and the matching conditions across the S-brane give us these relationships. So we know what the f of r does at the surface r0. So we know what these are, and we can compute the initial values of the cosmological scale factors to the future of the S-brane. But to compute what happens once you enter the cosmological phase, then you need to know the equation of state of matter. So the metric to the future of the S-brane is not universal, but it depends on what you assume for what happens to the matter, which is produced when the S-brane decays. And one idea is that the S-brane decays into a false vacuum state. In this case, what you find is you find the de Sitter space to the future of the S-brane. And you find exactly this space-time diagram. So you start with a black hole, you enter the horizon, you reach the surface where the Weyl curvature is equal to the string scale, you match it onto a cosmology with a T mu nu, which is given by vacuum, and you indeed find a de Sitter space. The second model is if you assume that the S-brane decays into radiation, and then what you find is that you find that this anisotropic cosmology does not expand very far, and you actually, this future phase actually becomes the white hole of a new universe. So this is what I wanted to say about the application of the S-branes to black hole topologies. So let me give you the overall conclusions. So I hope to first of all defined what I mean by the S-brane, and I've hoped to have shown you that with an S-brane we can obtain a continuous transition between a phase of ecpyrotic contraction and the radiation phase of expanding standard Big Bang cosmology. We can get this scenario is consistent with what we know about curvature perturbations, and it predicts a scaling band spectrum of gravitational waves with a slight blue tilt. And with the same S-brane idea, we can also mediate a continuous transition between the inside of a Schwarzschild black hole and something which initially looks like an expanding cosmology. So thanks for listening.
Okay, thank you very much for your very interesting talk. You present a lot of materials, so please, questions? Oh, yes. Igor, please.
Okay. Hello, Robert. Nice to see you again.
Yes, nice to see you.
Thanks for the very nice talk. My question is the following. From 30th last century, there are solutions like Tolman, Oppenheimer, Snyder, and others, which match black hole with the sitter.
That's right. There's a lot of work.
Can you emphasize what is new in your approach?
Oh, what is new here is using these S-Branes.
Okay, I have the question, a technical question about S-Branes. Could you write down Einstein equations for your action? How it looks like?
So you see, what I've done is the S-Brane is on the matter side of the equations. So let me go to this, to an initial slide. Right. So you see the way that I'm going to solve, I'm going to use the usual Einstein equations to the past and to the future of this time tau sub b. So and what I will do is across this surface, I will use the generalization of the Israel conditions to a space-like slice, which were worked out by D'Israel, by Doriel and Mukhanov, and also others. So are you happy with the technical answer to the technical question?
You don't consider dynamical as brains.
So I'm not modifying the gravitational equations in the bulk.
Mm-hmm.
I'm matching two solutions of the usual Einstein equations.
Mm-hmm. Now, do you claim that there are no singularities in your solutions?
Yes.
But you will, there is violation of energy condition.
Yes.
Okay. What
but it's a violation of the energy condition on a space-like slice.
Mm-hmm. Okay. Thank you very much.
Right.
Okay. Next question from Gabriel Veneziana. Please unmute yourself.
Yes, thank you. I unmute myself. Can you hear me?
Yes, please.
Okay. Hi, Robert.
Hi, Gabriele.
So I think it would be a wonderful idea to justify better the existence of this S-Brane. I mean, as far as I understood,
right.
You really postulate it.
That's
now,
right.
If I remember correctly, there has been some attempt by Kunas and co-workers.
That's right.
To really derive this S-Brane from string theory, but I forgot really what the situation was. Can you say something more about really justify? Because, okay, I agree that there will be more degrees of freedom coming in as you reach the string scale. If not for anything else, you know, the heavy string states will also come in. So, but how something so simple can emerge from a problem which looks so difficult?
Right. So so Kunas and collaborators actually justified it very much in the same way as I did, except that they were not using the string winding modes and string oscillatory modes as the new states. But they were saying, let's start with a theory with temporal T-duality, and then at the T-dual fixed point, they argued that new states will arise. And they then modeled it as the S-Brane.
I see.
So it's very similar to what.
But okay, okay, you model it, but
yes, I agree.
It's the simplest realization, I guess. I mean,
that's right.
For instance, has it to be infinitely thin? Or, you know, that's what I mean. Probably there is a whole high curvature phase which needs to be described differently from GR.
That's right.
So it's some kind of approximation, probably.
That's
or
right.
much more
But-
complicated, let's say.
So let me elaborate on your question, actually. So in everything I did in this section on the cosmology with the S-Brane, I've really modeled it as a delta function.
Yeah.
And now you could ask, how stable are the conclusions if you smear out this delta
Right.
function over string scale?
Mhm.
Because we know from other calculations that we've done is that if you construct a continuous bounce with
Mhm.
new physics, then you get different predictions.
I see. Then
I would actually like to see the S-Brane better motivated from fundamental string theory.
I see. So the statement is that if you smear it, you may change the predictions. Did I understand?
Yeah, I'm not sure about
you don't know.
aspect. I'm not sure.
Okay. Okay, thank you.
Okay, I see the next question from Alexei Koshelov. Alexei, please.
Thank you. Thank you very much, Robert, for a very interesting talk. I have one comment regarding the blue tilt, which you mentioned. In a paper which we have written some time ago with Sravan, with Alexis Tarabinsky and Anupam, we have shown that in principle, in higher derivative generalization of gravity, you can get blue tilt for inflation as such.
Yes.
So in principle, there are some other ways to gain blue tilt.
That's right. I agree. There's also,
this?
since there are quite a few people from Japan who are here, I should also mention that the Japanese group has pointed out that with G inflation, you can also get a blue tilt. So I would actually, in my defense, I would point out that this blue tilt, to my knowledge, the first real model for blue tilt was the model that Prof and I had, string gas cosmology. So there are various ways of getting the blue tilt. But you see, if there are different ways of getting the blue tilt, we have to go on and compute the next, for example, the running of the tilt.
Yes.
And we can do that.
Sure.
We have not done it for the S-Brane bounce.
Maybe, I'm not sure we can measure in some reasonable time, but compute, I believe, yes. And actually, I have a question. The question is, you mentioned that S-Brane is somewhere at the string scale.
Well, I motivated it from string theory.
Yeah.
And so therefore it's at the string scale.
Yeah, so my question is, what do you mean by string scale? How much is it in your construction? How is it related to Planck mass or whatever? So
in string theory, you have a string scale, which is a fundamental scale.
Yes, this I know, but
and it's related to the
Planck mass, and it's
via the dilaton. Now you see, I'm treating it as a. So there are two ways I could answer your question. One way is I treat it as a free parameter. The other way I could answer your question is I go back to the Bible of string theory of the 1980s, the Green, Schwartz, and Witten textbook, and I use the value which they use. Now the value actually determines the amplitude of the perturbations which I get. So if, for example, I use the value of the string energy scale of about 10 to the 17 GeV, then I will get an amplitude of the fluctuations, which is in good agreement with observations. If I would choose a string energy scale, which is 10 to the 18 GeV, then the amplitude of the perturbations will be too large.
Okay, so I mean, you have you mostly treat it as a free parameter, so you don't have something. So right. I mean, you cannot use your model to compute this.
No, but I can use if I treat it as a free parameter, I can use the data to fix it.
I see.
So I will use the amplitude of the density perturbations to fix it. And then I will get this scale of about 10 to the 17 GeV.
I see. Thank you.
Okay. More questions? Okay, please, Raman.
So I have one question, but before that, I have some small point to add what Alexei said. So, yeah, Robert, as you said, the inflation also can give blue tilt, but the way what we worked on is basically higher derivative generalization of stellar gravity, basically non-local generalization. So we modify the tensor power spectrum rather than scalar power spectrum. So I think the effect is different from scalar field models like G inflation. I just wanted to mention that. And I have a question here. During your talk, you mentioned that suppose you do not like string theory, you can construct some other way to realize this kind of slow contraction, or including bounds. I'm wondering, I mean, I cannot say I like superstring theory or not because my knowledge is not good enough, I believe. But suppose, like, if I want to get exactly the same kind of realization as you have, but I want to get it with some known physics. For example, take Higgs and some way coupled to gravity. And how can I get some contraction, slower contraction? Because from your talk, I understand it's only possible with negative potentials. But so I would like to take the known potentials like Higgs potential and add some kind of coupling to gravity. Well, with non-minimal coupling, it's Higgs inflation, but I don't know, maybe some new way to couple to gravity. I don't know. It's possible.
So you can easily get contraction with known physics. For example, the matter contraction scenario is just based on standard matter that we even can have classically. So it's easy to get a contracting phase. But now, if you ask, how do we get a phase of very slow contraction, ekpyrotic contraction?
Yeah.
That actually, the only way I know how to do it, but it is using a scalar field with a negative exponential potential. But I haven't thought very much about other ways of getting it. There are probably other ways of getting it, and it might be very interesting to explore. It would be very interesting to explore.
Yeah, because what I'm interested, then there's another question I am curious about, is the slow roll, ekpyrotic contraction, at what energy
It's not
scale?
slow roll. It's not slow roll. It's actually
it's not slow roll.
It's slow contraction.
It is slow contraction.
Not slow roll.
Okay. Sorry, I correct what I said. So it is slow contraction. At what energy scale it should happen in order to have exactly the scale invariant spectrum?
See, the amplitude of the spectrum is set by the energy scale of the transition from contraction to expansion.
Mm-hmm. And
so this is why
scale is it like a gut scale, or
it's gut scale, the heterotic string scale, so 10 to the 17 GeV. That's about the right.
Okay. I mean, in comparison with inflation, how long this contraction phase should last? Because in the inflation, it is 50 to 60 e-folds of expansion, but here in your case, how long this should last?
Yeah, I should be able to give you a number. I can't give you a direct number, but it's easy to work out.
Okay.
Because since you don't have exponential expansion, I'd first have to think about what is the analog of exponential expansion numbers.
Okay.
But the bottom line is that the scalar field doesn't have to roll for a long distance. The distance the scalar field has to roll is less than the Planck mass.
Okay.
Okay.
One last question, if I can. Yes.
Sorry.
Okay.
Okay, I finished, Shravan, or you want to ask something?
I have one more, one short question. I mean, in the inflationary case, we have post-inflationary reheating and particle production is quite, I mean, more or less understood, but I don't know how does it work in your case, because you have kind of negative potential, and how particle production happens in this picture.
Well, you see the energy density of stuff Oh, no. So you have to have a conversion between energy in the scalar field and energy in radiation.
Mhm.
So where did I have a reference? You see, if you form an S-brane, then the S-brane will decay. And in the reference that you see here, we've shown that the S-brane will typically decay into radiation. So the energy density in the contracting phase goes into the S-brane, and then the S-brane decays into radiation. So this is the analog of reheating.
Okay. There's also some temperature associated with the.
And it's given by the energy scale of the S-brane.
Okay.
And it's immediate, it's not. Thermalization will be quick.
Okay. The next question from Richard Kerner. Richard, please unmute yourself. Oh. Please unmute yourself. I cannot unmute you.
Maybe you can type your question in the chat.
Yes. Or maybe you switch on your
I'm
microphone.
sorry, I'm sorry.
Oh, now it's okay.
No, sorry, I'm sorry. What I wanted to say is that Einstein's equations are linear in the sense that you have energy momentum tensor on one side, and linearly depends on combination of curvatures. Right?
Yes.
There are no nonlinear terms. The Lagrangian is gravitational Lagrangian is still Einstein-Hilbert Lagrangian. But how can we be sure that there are no other terms at the very extreme conditions in Planckian scales?
Right. We cannot. So I have no answer to your question. This, if the string scale is much lower, is significantly lower than the Planck scale, then you might hope that
Yes.
the terms that you're worried about are negligible.
But even so, I would expect that there will be some contributions from Gauss-Bonnet term, for example.
Right. Right.
Yeah.
You know, this could be studied. So if you have a concrete model, then you could repeat the calculations that we've done, just instead of using the Einstein equations to the immediate past and future of the S-brane, you could use the modified equations. You would have to think about how would the matching conditions be modified.
Yes.
Do you know of any reference that's discussed that?
No, I tried to do something like that, but without brains. I mean, just with, that was a long time ago. With the nonlinear corrections, it's like Starobinsky, and but that was not done with brains, of course. It should be made, should be tried again.
Right.
No, thank
That's
you.
a very good question.
Thank you.
Okay. The next question has come from James Booth. Please.
Yeah, thank you very much for your very interesting talk, Robert. It kind of reminded me this part on black holes and this S-brane that sort of like interpolates between the interior of a Schwarzschild black hole and an asymptotically de Sitter universe, with some recent work that was done by Frolov and Zelnikov, who actually came up with this theory they call limiting curvature gravity, where they just insert basically Lagrange multipliers, but just not into the Einstein-Hilbert action, just not one, but two Lagrange multiplier fields to enforce an inequality, curvature inequality.
Now that I know very well. That work goes back to work in 1980 by Markov and Frolov and Mukhanov. In fact,
Right. So they show this explicitly. You know this literature much better than I do. I just wanted to comment that recently, a couple of months ago, they demonstrated this analytically for a two-dimensional dilaton gravity model.
That's right. That's right.
And I was wondering if, you know, because so like intuitively, what happens is that there is these Lagrange multiplier fields become dynamical at this supercritical regime, and the curvature exceeds this limiting value. And is there any relation, you think, between these Lagrange multiplier fields that become dynamical and these winding states in string theory that motivated this S-Brane formalism? Is it one way to think about this? Could they perhaps be an approximation to this behavior of these extra states that become relevant at these high energies, which is what you're trying to model with these S-Branes, as I understand?
Yeah, this is a very good question. So it would be interesting to look into that.
Okay.
Thank you.
More questions, please? If not, maybe I will ask a little bit general questions. As I understand, strings are very important in all of your construction. And we know very well that when we deal, better to deal not just with bosonic string, but better to deal with superstrings. I would like to ask you, can you see some footprints, some trace of a supersymmetry in your approach?
Okay, the answer is no. At the level that we've done our calculation, there is no trace of that. But you know the starting point is only self-consistent if we have supersymmetry.
Mm-hmm.
So otherwise, I would be motivating. I would be talking about an ill-motivated object. So I think if you want to justify the S-Brane from the point of view of string theory, I think it would be probably it would not work for bosonic string theory.
Mm-hmm.
Probably
Exactly.
you would have instabilities.
Mm-hmm. Okay, I understand. Thank you. More questions, please? If there are no more questions, let's thank the speaker again. Thank you very much, Robert. You presented very interesting talk with a lot of material. So thank you very much.
Thanks a
Thank
lot,
you again
Robert.
for the invitation.